All right, so we are now on 6.4, and today we're going to start getting into how to find the inverse of matrices and how we can use the inverse to help us solve problems in the future. So in the last couple of sections, especially like when we were doing all the Gauss-Jordan stuff, the goal was that was to solve a system of equations. So we're going to get into some other methods that you can use to solve a system of equations. We still might see some of that Gauss-Jordan stuff show up, and then we'll also talk about other ways that we can approach these problems as well. So we're going to talk about how to find the multiplicative inverse of a matrix, of a square matrix specifically. So a square matrix would mean it has the same dimensions for rows and columns. So like a 2x2, a 3x3, a 4x4. Something that's like a 3x2 matrix is not considered square because it doesn't have equal elements in the rows and columns. And then we'll talk about how to use inverses to solve matrix equations. And then we'll also talk about how you could use matrices to do like encoding or decoding of messages. All right, so I'm going to show you first how you would find the multiplicative inverse of a square matrix. Now think about just a regular number. The multiplicative inverse of a number is like the reciprocal of it. It's the number that you multiply it by to make it become a 1. So when we think about a matrix, we're kind of using that idea. When I have a 2x2 matrix like this first one, the identity matrix, which is this one here, is going to have 1s as the diagonal and 0s everywhere else, kind of like our end result that we wanted to have when we were working with that Gauss-Jordan stuff. We wanted our diagonals to be 1 and we wanted everything else to be 0s. That was really looking at the identity matrix. So when I take a matrix times the identity, it should not impact the answer at all. I should end up with the same numbers at the very end. And that's what they're showing you here. Now we've done this before where we've done our rows times our columns, and we write that all out. So we're just going to fill in this blank. This last blank would be us taking this row times this column. So it would be the 8 times 1 plus the 5 times 0. Okay. And then if you actually do this, like you start multiplying and adding, this becomes 7 plus 0, which is 7. This becomes 0 plus 4, which is 4. And then the last two elements are an 8 and a 5, which is the exact same matrix as I had to begin with. So that's how I know that the 1, 0, 0, 1 matrix is the identity matrix, because when you multiply it, it's not going to impact the answer. Okay, so down below, it also is showing you that it doesn't matter if you reverse the order of multiplication. Like if you put the identity matrix first and then you multiply, you still get the same answer. That's because multiplication is commutative. You can do it in any order, and the same thing happens for these matrices. So if you take the matrix times the identity matrix or you reverse it, it's not going to impact your answer. So this is what the identity matrix looks like for a 2x2. What do you guys think it would look like for a 3x3? Yeah, so it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. What do you think a 4x4 matrix would look like? Same thing, just you have more elements now. Okay, and we could keep going. We could make a 5x5, a 6x6, and all that. We probably in this class won't be getting anything beyond a 4x4 matrix. So we're not going to worry about a 5x5 or that. But that's what the identity looks like, okay? And again, that kind of showed up when we did our Gauss-Jordan elimination and substitution from like the very first section. This was like our end goal when we were doing those row operations. So you've already kind of seen this identity matrix. So now if we turn the page over, we're going to get into times that we need to find the inverse of a matrix. Okay, I'm going to give you a little bit of a shortcut here to finding the inverse of a 2x2 matrix. So over here where it says M equals A, B, C, D, that's just like a generic form of a regular matrix. Any 2x2 matrix will work like this. Those numbers or those letters A, B, C, D are going to be replaced by numbers. And so what we do to find the inverse is you're going to take the A and the D and you're going to switch them. So notice how these changed positions here. The A and the D just kind of did a little flip-flop there. The C and the B stay in their positions, but if you look over here, they're changing their sign. Now it says negative C and negative B, but don't take that as it means it's always going to be negative. The negative is symbolizing it's going to change its sign. So if it started out as a negative number, when you do the inverse, it's going to change to positive. And then on the bottom, this is something we haven't seen before. You're essentially cross-multiplying the elements inside of your matrix. You're taking A times the D and the B times the C, and you're subtracting. This is actually called the determinant, okay, which is kind of written underneath here. We haven't talked exclusively about determinants yet, but the determinant is when you basically cross-multiply in your matrix and you're subtracting. So similar to when you maybe solved a proportion, it's just there's a subtraction sign instead of there being an equal sign in between that. So the steps are to find your determinant, so do that cross multiplication and subtraction, flip your first diagonal, switch the signs of the second diagonal, and then you're going to divide every single element in the new matrix by the determinant. So let's take a look at this example. I've got the matrix 2, 5, 3, 4. First thing I do is find my determinant, so I cross multiply. So they're doing 2 times the 4 and 3 times the 5, and you're subtracting. So that becomes 8 minus 15, so your determinant is going to be negative 7. Then to find the inverse, you have to switch the 2 and the 4. So these got switched places. You can see how they wrote the 4 first and the 2 last. The 3 and the 5 stay where they are, but since they were both positive, they both become negative in the new one. And then we're dividing all of these new numbers by the negative 7. This right here, this final matrix with all those fractions in it, that's going to be the inverse of my 2 by 2 matrix. That means if I took the inverse times my original matrix, so I took the very first matrix I started with, times this matrix, I should get the identity matrix to show up. So the 1, 0, 0, 1. So let's practice one from scratch here. First thing I want us to do is find the determinant. So step 1, find the determinant. How do we do that again? Got 2 times 1 minus 3 times 5. So that would be 2 minus 15. So the determinant is negative 13. Okay, step 2 is we need to rewrite our matrix. How do we do that? Not negative 3. Oh, I'm sorry. Yep, negative 3 underneath it. Good. And then the last step is to just divide all those elements by the negative 13. If you could divide it nicely, do so. If you can't, though, you're going to have to leave it as a fraction. So this is going to be negative 1 over 13, negative 5 over 13, negative 3 over 13, and 2 over 13. So that would be the inverse of that original matrix. Again, if I multiplied those matrices together, I would get the identity matrix to show up, the 1, 0, 0, 1. Questions on finding an inverse of a 2 by 2? Okay, now what we're going to do is how do we find inverses if the matrices get larger? Okay, a 2 by 2 is not so hard. It's pretty easy to do those, I feel. But as you get into the larger matrices, it's not as cut and dry. You can't just follow the exact same steps that we did before. So we need to go over how do we do this. So what we're going to do is set up an augmented matrix with the right side equal to the identity matrix. So you can see down here, all of these numbers on this side would come from some systems of equations. So this would be like x minus a y plus a z, or sorry, no z there on that first one, and then so on. So they might already just give you the matrix there. But then if you notice on the right-hand side, it's a little bit bigger because they're giving you the identity matrix. The goal here is to basically get these to flip-flop. Like we want the left-hand side to become the identity matrix, and we want the right-hand side to do whatever it needs to do, and then that would give me my inverse. So we're going to do this by using those row operations again. So again, remember my goal is to get these numbers to all be ones, and I want everything else to be zeros. Now the first one is already a 1, right? So I don't need to worry about changing the first row number at all. But underneath that one, so this number here, I'd like that to become a 0. How could I do that? How can I make that 1 I circled in red become 0? So row 1 minus row 2? Okay, so let's go ahead and write that here. If I take row 1 minus row 2, that would say 0, -1. Watch your signs on this next one because it's 0 minus a -1, so that actually becomes +1. And then we still have to do that on the other side. So it'd be 1, -1, 0. Everything else about the matrix is going to stay the way it is. Okay. Now they want me to say, or they're showing you that row 2, column 1 is already a 1. So we don't need to really mess with that at all. Now what we want to do is figure out how do we make row 3, column 1 a 0. So how do I make this 6 here become a 0? Any ideas? Okay, so -6 times row 1, and then we're going to add that to row 3. So again, row 1 is not the thing that's being changed. It's row 3. So I'm going to rewrite row 3 here. So if I take -6 times 1, that's -6. Plus the 6 would be a 0. What would be my next element? It'd be 6 plus -2. Next one. -3. Next one. -6, right? Next one would be 0. And the last one? 1. Everything else stays the same, so I'm just going to copy these numbers down. Okay, so we've got 1s all the way down, or the 1 in the first one and then 0, 0. That's good. Okay, now what they're asking us to do is do row 3, column 2. So this 4, they want this to be a 0 now. How can I do that? Take the top row times 4. And then add it again to row 3. Good. Okay, so let's do that. 4 times row 1 plus row 3. I'll give you a minute to go ahead and just like fill in that bottom row on your own. And you know, I'm going to change this just a smidge. I'm going to take 4 times row 2 actually. Just because I don't want to really impact that 0 if I can avoid it. So by just making that little change, instead of using row 1, I'm going to use row 2. You take 4 times all of row 2, and then you add it to row 3. So I'm going to start doing that here. So I have 0, 0, 1, -2, -4, 1 for that last row there. Okay. All right, so we're getting closer here. Now I want to get row 2, column 3 to be a 0. So row 2, column 3 would be this one here. I want to make that a 0. How can I do that? You can use subtraction if you want. You want to just subtract a couple rows? So take maybe row 3 minus row 2, or you could take row 2 minus row 3. It doesn't really matter the order that you do that in. I'm going to do row 3 minus row 2 because that -1 that's in the middle, I'd like that to change its sign. And so if I do 0 minus a -1, it's going to force it to become positive. So 0 minus 0 is 0. Then this becomes a 1. This becomes a 0. All right, and then the last ones we got to think a little bit more about. -2 minus 1 would be -3. -4 minus -1 is -3. You got to watch your signs on that one. And then 1 minus 0 would be 1. Okay, so we are almost done. The last thing that I see an issue with is this term here. I want that to be a 0. So what can I do? Can you just, yeah, row 1 plus row 2. So this would say 1, 0, 0, -2, -3, 1. Everything else looks the same. Okay. And so now when I look at this, my 1s are diagonal, everything else is a 0. I've switched my parts of my matrices. I had the inverse originally on the right-hand side. I wanted it to be on the left-hand side. It is now. So this half of the matrix, which is written right down here, is going to be my inverse. Okay. Again, if I wanted to check that, if I multiply those matrices together, it should work out because they're inverses of each other. So that would be something that you could do if you wanted to check your work. I'm not going to go through that process of checking it, but that is how you would find the inverse of a larger matrix. So that would even work if you were working with like a 4x4 or a 5x5, like something larger than that, you would be able to do that same process. Yeah. So we're going to do one. This one kind of, gave us kind of some stepping stones for it. This one we're going to do from scratch. Okay. And this will probably be the last one that we get through today. So I'm going to start out by writing out the matrix, but then I also need to include the identity matrix on the other side. So you're going to draw that line down, and then it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we're going to start. First thing I want to do is I want to make this become positive. What's an easy way to do that? How can I just switch that sign? I think there's something even easier. We could just multiply by -1. Let's just switch the signs. So I'm going to take -1 times row 1. And so now it's going to say 1, -1, 3, -1, 0, 0. Okay. how can we make the 2 a 0? Well, remember, we can't just subtract a number. Like, we can multiply by a number, but we can't do the same thing with adding and subtracting. We have to subtract rows or add rows, maybe.
2 times row 3.
2 times row 3, and then
Minus it by row 2.
I think we'd want to add it,
Yeah.
right? Because if we take a 2 times a negative, then they're opposite signs. Okay, so this is going to impact row 2. So row 2 now, if I do these, would be 0, 1, 0. That's positive. And then the last one here would be 0, 1, and 2. Everything else stays the same. Okay, row 2 looks really good in my opinion because it says 0, 1, 0. That's what I want. So I'm going to try my best to not impact that if I can help it. But sometimes, we've seen in the past, sometimes you have to finagle it a little bit in order to get where you need to go. How can I make this negative 1 here at the bottom become a 0? Could we add it to row 1? Since they're opposite signs, I would add. Okay, so this would now say 0, 0, 1, negative 1, 0, 1. Okay, so now I think the bottom 2 rows look great. It's showing up as that identity, so now I just need to mess with row 1 a little bit. So how can we make this become a 0? Add it to row 2. So row 1 plus row 2. So it'd be 1, 0, 3, negative 1, 1, 2. All right, the last thing we need to do is take care of this 3. How can we do that? Yeah, perfect. All right, so row 3, we're taking times negative 3. We're adding it to row 1, so we should get 0, 0, 1. And then 3 plus a negative 1 would be 2. 0 plus 1 is 1. Negative 3 plus 2 is negative 1. And then everything else stays the way it is. So now that you look at the left-hand side, it's showing the identity matrix. So your inverse of matrix, I'm going to write a to the negative 1. That's how you would write an inverse of something, is using the negative 1. I'm just saying a. It could be any letter. You could name the matrix however you want. I'm just choosing a. And then you're going to put in these numbers. 2, 1, negative 1, 0, 1, 2, negative 1, 0, 1. There's your inverse. All right. Like I said, I think that's where we're going to stop for today, just because I don't want I don't want to get too far into the next stuff in case we don't finish it. So I wrote this wrong here. This should be a 1. So if you were confused on where that 1 went from, I think I just wrote a 0 by accident. But that should just be a 1 because when you do that last operation, it does not impact that 1.